Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 6th video lecture. And last time we left off talking about higher order derivatives, and that's going to lead into a fact we can say involving kind of an approximation for functions, certain types of functions using higher order derivatives called Taylor's theorem. Before I write and prove Taylor's theorem, which will be the majority of today's lecture, I want to remind you about some definition about a factorial and a fact, maybe with an example. And so first of all, let's start off with definition. Oops. For n being a natural number, n factorial is denoted by n with an exclamation point and given by it's equal to n times n minus 1 times 1 less than that. And we keep going down in this product to the last number that you have involved is 1. So as an example, you say, what's 5 factorial? 5 factorial is 5 times 4 times 3 times 2 times 1. And so numerically, this is 20, 60, 120. And if you do 6 factorial, it's going to be 720, so you can see that the number's getting big quick. And one other fact that I want to give about factorial is we do define 0 factorial is going to be equal to 1. So I call it a fact, it's more of a notational fact than anything, but we do define 0 factorial to be 1. Okay? Well, having reminded you, I believe it is a reminder, about factorials, we're ready to write up Taylor's theorem. So here's Taylor's theorem. It says, suppose f is a real function on the closed interval from a to b. N is a positive integer. F raised to the n minus 1, that means the n minus 1 derivative of f, is continuous on the closed interval from a to b. And the nth derivative of f exists for all t element of the open interval from a to b. We're going to let alpha and beta be two distinct points, of a to b. And we're going to define a function p of t to be equal to the sum as k runs from 0 to n minus 1 of the kth derivative evaluated at alpha, of this kth derivative of f evaluated at alpha, over k factorial times, here we're going to have t minus beta, t minus alpha, I should say, to the k. So that's a piece of t that's supposed to be defined. Then, so here's the conclusion. then there exists a point x. So there exists an x in, I should say an x between alpha and beta, okay, such that f of beta will be equal to p of beta plus the nth derivative of f evaluated at x over n factorial times the quantity beta minus alpha, and all that raised to the n. So that's the theorem. Okay. So, inserting this proof, I'm not going to write down that we're assuming all the hypotheses, but we are. And what we're going to do is we're going to let, so this is the first construction. And let me stop before I go any further. What I mean by construction, this proof has us look at certain things, and then do certain things with them, and then the result falls out. So, we're going to start off by looking at m. We're going to let m be the number defined by f of b equaling to f of beta equal to p of beta plus m times beta minus alpha raised to the n. And so that resembles the type of the conclusion of this Taylor's theorem statement. And what we want to show is that m needs to be equal to the right thing to get the conclusion. But before I do that, another part of the construction is we'll put a new function, g of t, equal to f of t minus p of t minus m times t minus alpha raised to the n, where a is less than or equal to t is less than or equal to b. So t's in between the closed interval, or is in the closed interval from a to b. Okay, and to get the conclusion we want to show that m is equal to the nth derivative of f evaluated at x over n factorial. That's what we want to show. And that way this fits the conclusion. And that's for some x between alpha and beta, where you remember by the hypothesis, alpha and beta are two numbers in A to B, closed interval. Okay, so first thing we're going to consider and observe is that note the nth derivative of of g is going to be, well, we're using the sum rule where we have minuses in front of the functions that are involved here. Well, it's going to be the nth derivative of f, which exists, evaluate t, for everything in between a to b, minus the nth derivative of t, minus, and here, this would be m times n factorial. We did the derivative of this n times. That's what we get. And that's the answer for this. Okay? Now let's look at P of t a little bit. P of t is going to be equal to, don't forget, that by definition, it's the sum as k runs from 0 to n minus 1. The k derivative, evaluated at alpha, all over k factorial, times t minus alpha to the k, which if we expand this, will be equal to, okay, so when k is equal to 0, this is the 0 derivative, so that's just f of alpha over 0 factorial, which is just 1. And then t minus alpha to the 0, that's just 1. So this is the first term. Plus, that's what sum means. Here we're going to have the first derivative of f evaluated alpha over 1 factorial times t minus alpha to the first. Plus, here's going to be the second derivative of f over 2 factorial times t minus alpha to the second. And we're going to keep going. Let me add 2 more terms. So here we have the third derivative, evaluated alpha over 3 factorial, t minus alpha to the third. And then finally, we keep going. This is equal. So plus, we keep going, plus the last term is going to be f to the n minus 1 alpha over n minus 1 factorial t to the t minus alpha to the n minus 1. And that's what we're going to get. Okay, now if you were to take the derivative, the nth derivative of t, what's going to happen is that all of these terms, these are polynomials in terms of, this should be 2. These are polynomials in terms of t. This is an alpha here. I don't know how clear that is. And it's a polynomial whose degree is n minus 1. And so when you take the nth derivative of it, you're going to get 0. That's what's going to happen. So based on what we said before, that means that when we take the nth derivative of g and evaluate it at t, that's going to yield really the nth derivative of f evaluated at t minus m times n factorial. That's great. And here we're thinking for a being less than t being less than b. Okay? And the reason we should be thinking that, I think I wrote something previously. Let me point to it. Incorrect here. Well, everything's fine, but here that's our derivative. The derivative, that's correct, what I got right here. The derivative at a or b for f sub n may not exist, so we're only defining for these t's. That's fine. All right, so remember what this means then is that if you were to solve for m here, well, let's say this. If this guy were 0, if you were to solve for m, if I could get this to be equal to 0 for some t in between a and b, then I'd have my result. Not between a to b, but alpha to beta, I'd have the result. So that's going to be my goal, is to show that there's some x in between alpha and beta, such that this part is 0. Okay? G, the nth derivative of g evaluated at x is 0. And then when you solve for m, you get f of the nth derivative of f evaluated at x divided by n factorial is what m is, and that's what we want to get. Okay? Let me write that up. So we want to show the nth derivative of t equals to 0 for some x between alpha and beta. Okay. Well, another thing to take notice of is that the kth derivative of p evaluated at alpha, that's going to be equal to the kth derivative of f evaluated at alpha, and that's true for all k equaling 0 up to n minus 1. And that can be seen by looking at what p of t is, taking its derivative, then evaluating alpha. And what will happen is when you take the derivative of p of t successive times, there will be a t minus alpha part to almost every term except the first term for that kth derivative. And so for everything but the first term of this kth derivative of p, you'll have a t minus alpha part being multiplied as a factor. So when you evaluate that at t equal to alpha, all of them will go away except the first term, and the first term is the kth derivative of f evaluated at alpha. Okay, so here's another thing, is that g of alpha itself will be equal to f of alpha, by the definition of g of t. It's f of alpha minus p of alpha minus m alpha minus alpha raised to the n. Okay, so this is 0. These two are the same based on what we've said here, and so you get 0. Then g prime evaluated alpha is going to be f prime evaluated alpha minus p prime evaluated alpha, and then this will be minus m times n times alpha minus 1. I'm sorry, it'll be alpha minus alpha to the n minus 1. This part is 0. These two are exactly the same by what's written here, and so you still get 0. And we keep going, and eventually we can say that the n minus 1 derivative of g evaluated at alpha, which is going to be equal to the n minus 1 derivative of f evaluated at alpha minus the n minus 1 derivative of p evaluated at alpha. This is an alpha here. And then here this will be minus m times, I think you can go ahead and say n factorial, but the last term is alpha minus alpha raised to the 1. And these two guys are the same, and this is 0, so you end up getting 0. Okay. What I'm thinking here, and I hadn't said this point, is that we know that alpha and beta are two distinct points in A, B, and what we're going to assume, let us assume that alpha is less than beta. Okay? And so here, so I'll just write that as a comment. recall how we've chosen M. So recall, or I'll just say since, M is the number such that it was f of beta is equal to, it was p of beta minus m times beta, I'm sorry, plus beta minus alpha to the n. Okay. Then g of beta, okay, well, that's going to be equal to f of beta, and then it was minus p of beta, and then it was minus m times, it would be t minus, because of the way that g was defined, it was going to be t, so it's beta minus alpha, because we're sticking in 4t beta raised to the n. Okay? And so here, this f of beta is exactly this, and so we get 0. Now, g of alpha was also 0. So, using the mean value theorem on g, using the mean value theorem, there exists an x sub 1, I'll say between alpha and beta, such that the first derivative evaluated at x sub 1 of g will be equal to g of beta minus g of alpha all over, here's x sub 1 minus, I'm sorry, this should be beta minus alpha. All right, now, but I know that g of alpha equals to 0 and g of beta equals 0, so this quantity equals to 0. Good. So we were looking kind of at the interval between alpha and beta, and now we can look at the interval between alpha and x. X sub 1, I should say. So look at that interval and then apply the mean value theorem to g prime. So using the mean value theorem, so here it is for g prime on a closed interval whose endpoints are alpha and x sub 1, we have that there exists an x sub 2 between alpha and x sub 1, such that g double prime acting on x sub 2 will be equal to, here I'll write down g of x sub 1, g prime of x sub 1 minus g prime of alpha all over x sub 1 minus alpha. And here, this was 0, so we get that this is equal to 0. Okay, so we get that this is 0. So g double prime is of x sub 2 is 0. We continue this process. Okay. We get g sub n, the nth derivative, g the nth derivative of g, evaluated at some x of n equals to 0 for some x of n between, it would be alpha and x of n minus 1. And so, we have that g, the nth derivative of g evaluated at x of n equals to 0, where x of n is between 0 and, not 0, but alpha and beta. Okay. And that's sufficient for m to be equal to the nth derivative of f, okay, evaluated at this x of n over n factorial. And that's what we needed. So that concludes Taylor's theorem, which is really a way of approximating certain types of functions with polynomials, that p of t. The next thing I want to do is turn to a different topic, and that is differentiation of complex value functions, complex functions. And so our discussion up to this point has been about differentiation of real value functions. So let's now look at this type of differentiation. So we're going to title this part of the chapter differentiation of vector value. That's what we call it. Vector value function. And here's going to start with a fact. We're going to let f be a complex function defined on the interval a to b, which is a subset of R. Then f of t, so t is in the closed interval from a to b, it's going to be equal to f sub 1 of t plus f sub 2 of t, two distinct functions, times I, for some real functions f sub 1 of t and f sub 2 of t, where, if you recall, I is equal to the square root of minus 1. And so this is saying that any complex function defined on a subset of R can be broken down into a function that yields the real parts of the imaginary numbers for the output, and a function, a real value function, that is associated to the imaginary part of the output values of f of t. So next we're going to look at the definition of the derivative of this type of function. So we let f be a complex function on AD. Okay. Then derivative of f at x is denoted by f prime of x, and given by our usual definition, which is the limit. So here we say f prime of x is equal to the limit as t goes to x of f of t minus f of x all over t minus x, okay? Provided this limit exists. Now, here we're working with complex numbers, and so we're talking about a limit of complex value function, and so it's good for us to spend just a little bit of time recalling about that metric on the complex numbers, the usual one. So that's what we're going to do next. So recall, if z and w, so z bar and w bar, are two complex numbers, with z bar equaling to z1 plus z2i, and w bar equaling to w1 plus w2i, where z1, z2, w1, and w2 are all real numbers. Then, when we're talking about the metric on the complex numbers between z bar and w, that's going to be equal to the square root of z1 minus w1 to b squared plus z2 minus w2 to b squared. So this is the usual metric. On complex numbers. Okay. So here's the fact. It says let f be a complex function defined on a to b, and we're going to say that f of t is equal to this f sub 1 of t plus f sub 2 of t times I, with t being in this closed interval. So we let x be an element of a to b. Then f prime of x exists if and only if f sub 1 prime of x exists and the first derivative of f sub 2 of x exists. And that's not all. Moreover, what we get, if f prime of x exists, then f prime of x is equal to f sub 1's derivative evaluated x plus f sub 2's derivative evaluated x times I. So we want to prove this statement. It's a nice result. It gives us a natural way of taking the derivative of a complex number, a complex function. When you break down the complex function into its real function part and imaginary function part. So here's the proof. We'll let f be a complex function defined on AB and f of t be equal to f sub 1 of t plus f sub 2 of t times I. We're going to let x be an element of the closed interval from A to B. And now we're ready to get started. And we'll go in this direction first. So here, suppose that f prime of x exists. And so since it exists, it's going to be equal to a complex number. Say f prime of x is equal to some number a plus bi. We want to show that f sub 1 prime of x is equal to a and f sub 2 prime of x is equal to b. Okay? That is, we want to show both. We want to show that the limit as t goes to x of f sub 1 of t minus f sub 1 of x over 2 minus x equals to a, and the limit as t goes to x of f sub 2 of t minus f sub 2 of x over t minus x equals to b. That's what we want to show. Okay, so we're talking about limits in a metric space of a function. So here, what we're going to do is we're going to use the definition of a limit of a function. And so that's going to involve us considering an epsilon greater than 0. So we're going to let epsilon greater than 0 be given. What we need is we need a delta bigger than 0, such that for all t in the closed interval from A to B with 0 being less than the absolute value of t minus x, so the absolute value is this usual metric in R, is less than delta, then the absolute value of f sub 1 of t minus f sub 1 of x over t minus x minus a will be less than epsilon. And also the f sub 2 of t minus f sub 2 of x over t minus x minus b will be less than epsilon. So we'll show both of these things. And here's the reason we can do it is since f prime of x exists, and let's write it this way. So we know f prime of x is equal to the a plus bi. That's what we got. Since that is true, then we have the limit as t goes to x definition of f of t minus f of x all over t minus x is equal to a plus bi. So there exists a delta greater than 0 such that for all t elements of a to b with 0 being less than the absolute value of t minus x being less than delta, then, okay, so we write this in terms of that metric. Well, I'll leave it in the abstract sense of that metric. So the metric on C between f of t minus f of x, all over t minus x, the distance between that and a plus bi will be less than epsilon. Okay, well, let's look at that metric a little bit more. So, for all t element of a to b with 0 is less than t minus x is less than delta, we have the distance in the complex plane between f sub 1 of t plus f sub 2 of t I minus f sub 1 of x minus f sub 2 of x I all over t minus x. That distance between a plus bi is less than epsilon. What is that? Well, first of all, which implies, so we have, I'll just say which implies, okay, that this distance between f sub 1 of t and f sub 1 of x over t minus x, then plus f sub 2 of t minus f sub 2 of x over t minus x, and this is times I, the distance between that and a plus bi is less than epsilon. And so here, when we talk about taking the metric for this part, this is the real part and real parts, and so that implies that the square root of f sub 1 of t minus f sub 1 of x over t minus x minus a to be squared plus f sub 2 of t minus f sub 2 of x over t minus x minus b, that to be squared, will be less than epsilon. And I'm just applying this usual metric. So, let's note that epsilon will be greater than exactly what I have written previously, so I'm just going to write it down again. B squared plus, and here's the f sub 2 of t, minus f sub 2 of x, all over t minus x, minus b to b squared. And so that's what we have just written. But I'm going to say this, what I just wrote, is greater than or equal to this part. So I'm dropping this part here, and so when I drop it, I get something smaller. But this is nothing more than the absolute value of f sub 1 of t minus f sub 1 of x, all over t minus x minus a. And so we have that this part, let's write a sum in here. We got what we wanted. So for all t elements of a to b, with 0 being less than t minus x, being less than delta, we have f sub 1 of t minus f sub 1 of x, all over t minus x minus a is less than epsilon. So that says the limit as t goes to x of f sub 1 of t minus f sub 1 of x over t minus x equals to a, and that's what we wanted to show. Okay? And so that says thus f prime of x equals to a. So it exists. I'm sorry, f prime sub 1. F sub 1 prime of x exists. We can do the same thing for the f sub 2's, and I'll just write that up very quickly. Similarly, epsilon is going to be greater than, so it's the f sub 2 of t minus the f sub 2 of x, square root of this, all over t minus x minus b squared, which of course is equal to the absolute value of f sub 2 of t minus f sub 2 of x, all over t minus x minus b. So, for all t elements of a to b with 0 less than t minus x less than this particular delta, we have f sub 2 of t minus f sub 2 of x all over t minus x minus b is less than epsilon. So what that says is that the limit as t goes to x of f sub 2 of t minus f sub 2 of x all over t minus x equals to b. And what that is saying then is that f sub 2 prime of x equals to b, and that's what we want to show. F sub 2 prime exists. Just a little bit more to go in this proof. It is an if and only statement. But we aren't quite through with the first part, but we're very close. At the end of the first part, then f prime of x is equals to the limit as t goes to x as t goes to x of f of t, I'm sorry, yeah, I would say it. So f of t minus f of x over t minus x, which equals to the limit as t goes to x of f sub 1 of t minus f sub 1 of x all over t minus x plus f sub 1 of t minus f sub 1, I'm sorry, f sub 2. F sub 2 of x all over t minus x times I. Okay? And so, since this limit exists and this limit exists, we can take the limit of each one of them is equal to, this is f prime, f sub 1 prime of x, plus this will be f sub 2 prime of x times I. Okay. Now, going in this direction, I'm going to use some of the work we just wrote. And so here, suppose f sub 1 prime of x and f sub 2 prime of x exist, then f prime of x in general, which is equal to what we just said was the limit, let's see if this exists, as t goes to x of f sub 1 of t minus f, well, it's f sub 1 minus f sub 2 plus f sub 2 of x, f sub 2 of t, and we're doing the right thing, times I, minus f sub 1 of x, minus f sub 2 of x times I, all over t minus x. And then we can split this up. This is what we did a second ago. Is equal to the limit as t goes to x of f sub 1 of t minus f sub 1 of x all over t minus x plus the limit as t goes to x of f sub 2 of t minus f sub 2 of x all over t minus x. This is times I, pull the I out front, is equal to the limit as t goes to x of f sub 1 of t minus f sub 1 of x all over t minus x plus I times f sub 2, well, I should write down limit as t goes to x of f sub 2 of t minus f sub 2 of x all over t minus x. And that's equal to f prime, f sub 1 prime of x plus f, so 2 prime of x times I. That's what this is. So that says f prime of x exists. Okay. So since, I'll just write this conclusionary statement. Since f prime of x exists, if and only if, exists, if and only if f prime, f sub 1 prime of x and f sub 2 prime of x exist, okay, and what we have is, well, that's the conclusion. We have that it's equal to, the derivative of f is equal to the derivative of each part added together, multiplied by some part multiplied by I. So that's our result. Okay, that's enough for this lecture. Thank you very much for your time and patience.